This video is prepared by Avya Classes. Please subscribe the channel, raise your doubt and watch the video for sure success in JEE, AIMS and NEET. Position and velocity of an automobile under constant power. So in this section we will check that if a body is under constant power, then how its velocity and position changes with respect to time. So basically we will find out that what is the velocity, which is the function of time, and similarly the position is the function of time under the condition of constant power. So let's start for this, and first we will do the calculation of velocity. So as we know that the power is defined as F dot V, it is constant. So basically F into V is equal to constant factor, and we denote it by P. Now as we know that the acceleration will be denoted by, or the force is given by, m into a, where a can be written into two forms, that a can be written in the form of either dv by dt or v into dv by ds. If you don't have idea about these two, you just go through my class of motion in a straight line to get a more idea about it. So if I write the value of force is equal to m into dv by dt into v, then it will be equal to p, which is a constant. So now we will integrate it. So basically on the left hand side we will get the v into dv, and the right hand side we will write p by m into dt, and basically we will integrate it. So how we will do this integration? So basically our term is v into dv, and on the right hand side is p by m into dt. So basically if you see that on the right hand side this factor is constant, so we can take it outside the integration. So basically we are integrating time. So if time is equal to 0, then at point of time the velocity will be equal to 0, as the particle is starting from rest. So at t is equal to 0, on the left hand side v is equal to 0, while at the time t we have a velocity equal to v. So those having no idea about integration, so I just note down formula here, that if I integrate xn, then its value is xn plus 1 divided by n plus 1. So based on this formula, it will be equal to v square by 2, and limit is 0 to v, and the right hand side it is p by m into t. So from there we get v square by 2 is equal to pt by m. So basically this is the value. Actually I have done it through the indefinite integration. So in case of indefinite integration, we just put one constant factor c1, and the value of c1 is calculated based on the condition, and here the condition is that the particle has been started from the rest. So if I put the condition that when t is equal to 0, velocity will be 0, which implies that c1 is equal to 0. So we can get this value, that v square is equal to 2 pt by m, from both ways. So if I put in this, that when t is equal to 0, then v square, then v is equal to 0, so 0 plus 0 is equal to 0 plus c1, and from there we get c1 is equal to 0. So basically what we get v square is equal to 2 pt by m. So v is equal to 2 pt by m square root. So basically we came to a conclusion that velocity is directly proportional to t raised to the power 1 by 2. So if a particle is moving under constant power p, then its velocity will be directly proportional to a square root of time. Similarly, we will calculate how the position of particle varies with respect to time. So as we have already defined that the velocity is equal to twice pt by m and square root of it. So basically we may write velocity is equal to ds by dt. That is, velocity is the rate of displacement, that is the change, that is the displacement with respect to time. So basically ds by dt is equal to 2 pt by m raised to power 1 by 2. So if we integrate it, we will get the value. So either we can approach the indefinite integration or the definite integration. I will show both separately. So ds is equal to 2p by m raised to power 1 by 2 t raised to power 1 by 2 into dt. So if you integrate it, then first through the definite integration, first through the indefinite integration without putting any limit for this. So if you don't put any limit for this, then if you integrate, then the left hand side it will become s, and on the right hand side it will become 2p by m raised to power 1 by 2. And if you integrate t to the power 1 by 2, then it's equal to t to the power 1 by 2 plus 1 divided by 3 by 2. So 2 by 3 t to the power 3 by 2. So we get 2 by 3 into t to the power 3 by 2 plus c2. Now if we put the conditions, then we get the value of an arbitrary constant c2. So if we consider the position of particle be 0 at time t is equal to 0, then if I put the value of t is equal to 0, s is equal to 0, we get c2 is equal to 0. So what is basically our condition? Our condition is that the particle is under a constant power p, under a constant power p, and it starts at t is equal to 0, and its initial displacement is equal to s is equal to 0, and we have to calculate the velocity and displacement s at time t. So basically we get s is equal to 8p by 9m raised to power 1 by 2 t to the power 3 by 2. So s is directly proportional to t to the power 3 by 2, and if I do it through the definite integration, then at limit t is equal to 0, s is equal to 0 as per this figure, and at limit t, when the time will be t, then the displacement will be s, and we get the value is equal to s is equal to 2p by m raised to power 1 by 2 into 2 by 3 t to the power 3 by 2. So the answer comes same. So basically from this discussion we make a conclusion that if a particle is under constant power, then displacement or the position is proportional to t to the power 3 by 2, and velocity is directly proportional to t raised to power 1 by 2. And this is the important concept. Sometimes problem asked based on this concept. On work energy theorem using power. So as we know that from the work energy theorem that the work done by all forces is equal to change in kinetic energy. The forces can be conservative, non-conservative. So basically work done by all forces W net is equal to change in kinetic energy, that is Kf minus Ki. And we have also learned that the value of work done is equal to, in fact we know that the power is equal to dW by dt. So from there we get dW is equal to P into dt. And if we integrate both sides, then on the left hand side we get W, and work done is equal to integration of P dt. So basically from there we can come to a conclusion that Kf minus Ki is equal to integration of P dt. So this formula is of immense importance, and when the power is constant, suppose that the power is constant, then we can take this P outside. So if the power is constant, then we take Kf minus Ki is equal to P integration of dt for constant power, and if I limit it from 0 to t, then we get Kf minus Ki is equal to pt, which is the equation written here. So what is the example of this? Suppose that a body is under the power, suppose 10 watt. A body is under the power 10 watt, and you have to calculate the change in kinetic energy during the time 5 seconds. So t is equal to 5 seconds, p is equal to 10 watt. Here the power is constant. So what you will do it, you have to calculate the change in kinetic energy. So change in kinetic energy is simply the multiplication of power into time t, and from there we get change in kinetic energy is equal to 50 joule. Again, as the power is in the positive, so clearly the work done by work done on the body will be positive, and it will increase its kinetic energy. So now what is the basic use of this? When the power is not constant, the power will be variable, then this formula will be very much handy, and we have to use a concept of calculus to solve it. So I will give you one example of this. Suppose that the power will be a function of time t given by p is equal to kt. Suppose that the power, suppose a body is moving on this surface where the power is not constant, power is equal to kt. That is, when t is equal to 0, we have 0 power. However, power is increasing on the time increases. So suppose when the time t is equal to 2 seconds, the power is equal to 2k, where k is some arbitrary constant, and however for some time t is equal to 5 second, the power is equal to 5k. So clearly power is increasing. So in this case we cannot take p outside the integration. So what will be our approach? Our approach will be delta k is equal to p dt, and suppose you have to calculate the power during the time t, then what you will do? So you just write the value of power kt and dt. You have to calculate the change in kinetic energy during the time t. So you just take limit 0 to t, and if you integrate it, you will get the value equal to kt square by 2. Limit will be 0 to t, so the answer will be kt square by 2. So change in kinetic energy is equal to kt square by 2, where k is an arbitrary constant. So from there you may see that the change in kinetic energy is not constant. It depends on the time. So clearly the work energy theorem can be associated with the power concept, and with this we can get the actual change in kinetic energy when a power is applied on a body.